or three solutions or two or three phases or two or three elements into a single mixture. Okay, single mixture, and the output of it will be an alloy. Okay, the output of it will be an alloy. So here if you see in alloy structure there are two types. One is a single phased alloy structure, which we call it as a homogeneous format of alloy structure, and in that another phase we call it as mixture. Mixture is will be having several phases. Okay, combination of several solid phases into a single phase, we call it as a mixture alloy mixture format. And here if you see it, you are having different formats like pure metal, solid solution, compound, etc. Many formats are there. These things we have seen in the last class. Okay, and here in the homogeneous format we have two categories. One is a solid solution category, wherein we have two types. One is a substitutional and the other one is a interstitial. Substitutional is nothing but one element will be entering the space. One element will be entering the space in the space of the another element. It will be substituted. One element will be substituting the another element. Okay, and the next one is the interstitial element. What the alloy mixture is, sorry, alloy homogeneous structure is, wherein the interstitial format. Are you able to visualize my see my
Yes,
screen?
sir. Yes,
Yeah,
sir. Yes.
yeah. In the alloy format, one element will be substituted by the other element in substitutional format of solid solution. And interstitial format of solid solution, what happens is wherever there is a space in the atomic structure, in that space and another element will come and sit. Okay, come and occupy. Okay, that kind of solution we call it as a interstitial solid solution. Then we have many intermetallic compounds. Okay, as we have discussed, and which is not on our scope, like intermetallic, interstitials, and electronic compounds are there. Okay, so these things we have seen it in the last class. And today what we are going to see is we are going to see about the phase diagram. Okay, we are going to see the phase diagram. Phase diagram is also called as an equilibrium diagram. Okay, or we can also call it as constitutional diagram. Mainly, what is phase diagram? It so when the temperature changes. Okay, when the temperature, when we heat a material or when we cool that material. Okay, that is at various temperature and at various composition. Okay, for composition of the material, if you take how the material will behave. Okay, how the material will behave, what will be those properties. Okay, how the phase of the material, that is from solid to liquid, liquid to solid, or solid plus liquid. So how the phase of the material will be changing. Okay, everything we will be plotting it in a curve. Okay, in a graph. That plot, that graphical representation, wherein the various phases will be present in the material system at a particular temperature and a composition point. Okay, so that is what we call it as a equilibrium diagram or a phase diagram. So when you talk about this phase diagram, what we will be having it in y-axis is, sorry, in the x-axis we will be having the percentage composition, and in y-axis we will be having the temperature. And if you plot a point between x and y, at whatever the point in the plot you get, that will be the phase of that particular structure. Okay. Now, apart from this, there are different other uses for a phase diagram. Like it shows the various phases present in a particular composition or temperature, or it indicates the solubility of one element. Okay, how in particular temperature or in a particular condition, how whether the one element is soluble in the other. Okay, or in what temperature range the metal will either be solidified or liquefied. Okay, or in what temperature the metal will start melting. Okay, so these kinds of data. Okay, these kinds of data, whether it will be a saturated or super saturated, everything, these kind of data we will be getting it with respect to a phase diagram. So for that we will be using the phase diagram. Very important aspect. That is what is called as phase diagram. Now coming to the different categories of phase diagram, different types of phase diagram. Okay, the different types of phase diagram will be based on, just a minute. Yeah, the different Gauri Shankar, have you came? Gauri Shankar, Gauri Shankar.
Yes, sir.
Okay, 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 right. Both are present. Okay, fine. So different categories or types of phase diagram is based on the solubility of a component. Okay, based on the solubility of a component in the liquid state, it is classified. Okay, first category, if you see the components, the components which we are going to mix it to form a solid solution. That's what we are talking about. So the component should be completely soluble in the liquid state. Okay, first category is that. Okay, first category is that. In that we are having subcategories. That's the first category is the component should be completely soluble in this liquid state. That is the first condition. Simultaneously, it should be completely soluble in the solid state also. Okay, that is type 1. Okay, if any particular compound satisfies these two categories, it will be falling under the type 1 category. Next is, it is insoluble in solid state but only soluble in the liquid state. Soluble in the liquid state is a condition. Okay, that is a condition. So that but it is insoluble in the solid state. So that we call it as eutectic type of thing. Okay, that eutectic, we call it as eutectic reaction. Okay, that is nothing but type 2. Next category is, you fix this as constant, that is soluble in liquid state is constant. Next category is partly soluble in the solid state. This is also an eutectic reaction only, but it is type 3. We call it as type 3. But in the fourth category, what happens is, it will be soluble in liquid state, but in solid state, what it will be forming it is, it will not become completely soluble. It will form an intermediate phase. It will form a intermediate phase. Okay, so that intermediate phase, if it becomes reactive, we call it as pretectic reaction. We call it as pretectic reaction. So these are the various five types of the first category. Second category is, components are partly soluble in the liquid state. Partly soluble in the liquid state, that we call it as monotectic reaction. That we call it as monotectic reaction, type 6. Then components are insoluble in the liquid state and insoluble in the solid state. That we call it as type 7. The next one is transformations in the state. Okay, transformations in the solid state. How it is getting transformed. Okay, whether allotropic changes happens, or in the atomic structure order changes, or any eutectoid reaction or pretectoid reaction takes place. So based on that, the phase diagrams will be classified. Okay, first type of phase diagram is a one component system. One component system is simply a very simplest form of phase diagram, which will be having only one component. Okay, as I told, we will be having a pressure. As we will be having the pressure along the y-axis and temperature along the x-axis. So what happens is, when a particular water is heated above this 100 degrees Celsius, it will become a vapor. Okay, above it will become a vapor. So within this region, so when it is brought below sub-zero, it will sub-zero degrees Celsius, it will become a ice. Okay, it will become a ice. Okay, so this region we call it as water vapor, wherein we don't apply any pressure, but only within this portion. Okay, in this portion it will be water vapor, but above that and below, by applying some in the atmospheric pressure conditions at low pressure, it will be in a form of a water, but below sub-zero degrees Celsius, it will be in a form of a ice. So all the three curved lines will be meeting at a coincident. Okay, all the three faces will be coinciding at a point called triple point. All the three faces will be coinciding at a point called triple point. Okay, this kind of one component phase diagram, we call it as water phase diagram. Okay, water phase diagram. A very simplest form, wherein we have only one component, and it is the simplest form of phase diagram. Okay. Next is binary phase diagram. Here in the binary phase diagram, either the system should be completely soluble in solid, or it should be completely soluble in the liquid. Okay, that those kind of components only can be used to draw the binary phase diagram. Can be drawn with the help of a binary phase diagram. So that kind of systems, just a minute. That kind of system we call it as isomorphous system. Okay, here in isomorphous system, what happens is, the pure components, okay, the pure components will melt at a will melt at a single temperature. Listen carefully. Pure components will melt at a single, what you can say, single temperature. Pure component or pure metals, if you take, it will be having only one melting point. But alloy, as I already told, it is a mixture of two or three elements. Okay, it is a mixture of two or three elements. So it will be melting over a range of temperatures. Okay, starting from a melting point of one element to the melting point of the other. Okay, over a range it will be melting. Okay, but it depends upon the composition. It depends upon the composition also. That is which metal is in the higher percentage or which metal is in the lower percentage. That composition also is very important. Okay, that composition plays a very important role here. Okay, in the case of isomorphous system, only if it if it is an isomorphous system, we can go for this binary phase diagram. The reason why we call that it as an isomorphous system is it will be a single type of simple type or single type of crystal structure only, but the ratio of the but all the ratio, okay, but all the ratio will be similar. Okay, all the ratio in the solid solution will be similar and it will be in similar proportions. Okay, only those we call it as isomorphous system, and that component we call it as a isomorphous component. Okay, so for that isomorphous system only we can draw this binary phase diagram. Okay, here as I told, the solid mentioned should be a crystalline solid. For a binary material, a crystalline should be crystalline solid. So see here, this is a composition of a material and this is a temperature. So in the normal temperature, the component will be solid. Okay, the component will be solid. So when you increase the temperature, okay, when you increase the temperature in a well-defined position condition, okay, well-defined composition within the composition with a level of liquid, okay, well-defined, okay, both the solid and the liquid state should be in the equilibrium. Okay, it should be in the equilibrium. Okay, in that cases, if it is heated beyond a further temperature, if you heat it beyond a particular temperature, it will become vapor. But in the normal stage, it will be in the solid solution. When you heat it, it will become a liquid solution. After a particular temperature, it will become a solution. So but in between it will be in a form of a solid plus liquid mixture. Okay, it will be in a form of a solid plus liquid mixture. That is, if the component is zero, if component is 0 or 1, up to a particular point it will be there. In the next point itself, it will be changing to liquid. But if you increase the composition of that particular element, what happens is the point that there will be a separate region which will be forming, and that separate region will be intermediate between the solid and liquid. Okay, which will be in the format of solid plus liquid format, and after that only it will be converting to liquid solution. Okay, so that is between the two phase regions. Okay, phase regions of an alloy, there will be a special region or a special portion that we call it as solid plus liquid mixture. Okay, are you listening? Hello, hello,
Yes, sir.
are you listening?
Yes, sir.
Hmm. Yeah. So how we can develop these phase diagrams? Okay, how we can develop these phase diagram? For the development of phase diagram, there are many techniques. One is a thermal analysis technique, wherein we will be simply heating the component to a required temperature, and we will be finding it how it phases changes, how it properties changes, everything we will be marking it and finding it. Next is metallographic method. Metallographic method is nothing but instant cooling. Okay, instant cooling, instantly cooling the component from the. Just a minute, I will drink water. Yeah, instant cooling means from a particular state. Okay, from a particular state, it will be instantly cooled. Okay, by either dipping it in a cooling medium or dipping it in ice cold water or something like that. By dipping it in a particular medium or a thing, instantly we will cool it. But and we will be seeing its phase change. But the only difference is here a skill is required. Okay, directly we cannot do it. Considerable skill is required to do these kind of thing. But it can be used for verifying the already existing diagram, but for creating a new diagram, it is not that much efficient. Okay. Next, the last one is a XRD. XRD is nothing but a X-ray diffraction technique wherein you will be using a Bragg's law. Okay, as the basic principle, n lambda equal to 2d sine theta. And based on that n lambda equal to 2d sine theta, we will be measuring the lattice dimensions. Okay. Okay, lattice dimensions can be measured. From the lattice dimension measurement, we can do the solubility analysis or changes in the phase analysis with respect to the temperature. Okay, with respect to the temperature, we can do it. Okay, so that is what these are the various methods of developing a phase diagram. Okay, so this is another in a binary phase diagram itself. we are how to construct a binary phase diagram is it's very easy. What you have to do it is first plot a temperature and a diagram plot. Okay, what happens is take a different five or six compounds. Okay, in such a way that first A is zero, percentage of A is zero, percentage of B is 80, sorry 100. Similarly, 20, 80, 40, 60, 60, 40, 80, 20, 100, 0. Go on increasing one and go on decreasing the other. So mark the curves of, okay, that is what you can say, cool every component from a particular temperature to that particular to another particular temperature. Okay, mark the cooling curves. Okay, mark the cooling curves, the points which are traced. Okay, the points which are traced by a particular path. Okay, the points which are traced by a particular path, that is, for example, if there is a steep peak, okay, there is a steep peak, suddenly its slope changes, then it comes down again. Okay, the portion which is traced, okay, if you mark the upper and the lower points of the phase slope changes wherever you happens, if you note it down and if you join it with an ellipse, okay, so this center portion only we call it as liquid plus solid solution. Okay, liquid plus solid solution, the portion where the material exists in the form of liquid and solid. Okay, so that is continuously seriously, okay, in a series, drawing the cooling curves, okay, with increasing the percentage of one and decreasing the percentage of the other, and then find the portions where the in between portions where the slope changes drastically. Okay, so that is the point. Then connected to form a elliptical kind of structure, and in that region the material will be behaving like a solid plus liquid mixture. Okay, solid plus liquid mixture. Okay, so this is what the phase diagram of two metals completely soluble in the liquid and the solid state. So if you can see this series of cooling curves for different alloys in a completely soluble system, both liquid and solid state. Okay, so these are the examples. Now some of the examples, one example is the, okay, here Cr2O3. Okay, one example is Cr2O3. Many types of isomorphous systems are there, like copper, nickel, silver, gold. Okay, silver, gold, or germanium, silicon. Okay, Al2O3, Cr2O3, like that. Many combinations are there. And one more thing I forgot to say, the region. Okay, the line which is separating the solid plus liquid solution and the solid solution is called as solidus. Okay, this line is called as solidus, and the line which is separating the liquid solution with the liquid plus solid solution is the liquidus. Okay, so these are the examples of this copper nickel. Just a minute. Yeah. Okay. So that line which is there, which is separating, we call it as solidus and the liquidus. Now, if you see this example is Cr2O3 mixed with Al2O3. Okay. Now, if you see here in this portion, it will be behaving like a solid. Now, if you see a crystal structure, it will become like a solid, and above this, you call it as a liquid structure above that, what you can say, above the liquidous line. Okay. Okay, see here, not a line, liquidous line separating L and L plus. L means liquid, and this is liquid plus solid mixture. And if you take, this is a solidus, which is the solid region. But if you see in between, it will be a mixture of both, mixture of solid and liquid mixture. Okay, this is an example. And the thing is that to mix copper and nickel, okay, to mix copper or nickel, or to mix Al2O3 or Cl2O3, we have already in the last class itself we have seen. Okay, we cannot take to any of the elements. Okay, whatever the elements we like. Okay, whatever the elements we like, we cannot take it and we cannot mix it. Okay, it should satisfy Hume-Rothery rule, and then only we can take it and we can mix it. Okay, that is the important thing. Okay, next coming to binary phase diagram itself to continue further. If you see, if you are taking two components and that two components melt at a single temperature itself. Okay, melt at a single temperature itself. Oh, but alloys we have seen that it will be melting over a range of temperature. Okay, over a range of temperature it will be melting. Okay, these stories and all we have already seen. Okay, liquid in binary phase diagram, what I told, there are two phases. One is a liquid phase and the other one is a solid phase, and in between we will be having a solid plus liquid mixture. Okay, but we cannot call it as a semi solid state. That is very important. This phase, okay, I forgot to say, this phase we cannot call it as a semi solid state. Okay, it is a liquid plus solid state. Okay, because fixed composition of the structure and these things are there. Okay, in a single phase system means the composition of alloy is only the composition, but in two phase alloy it's not just a composition, it will be affecting the phases also. Okay, that only in two phase region where the composition is affected by the phase. Okay, for those kind of systems only we will be considering the lever rule. Okay, we will be considering the lever rule. Lever rule, we will see what is lever rule later. Lever rule will be having a link between the number of phases formed and various number of compositions. Okay, now if you see, this is a there is a principle called tie line and lever rule. Okay, tie line and lever rule. For example, okay, here as I told you, here I am having a percentage composition of a particular element, and here I am having a temperature. Okay, now I am taking a random temperature C0, which is in equilibrium. Okay, C0 at T0, if you see, okay, at T0, C0 is here, T0 is here. At T0, if you see, it will be in a liquid plus solid medium. Okay, it will be in a liquid plus solid medium. Only that kind of point we call it as the equilibrium point. Okay, equilibrium point. Now, if you take C1 and C2 correspondingly, if you take C1 and C2, C1, okay, randomly take C1. C1 is nothing but a point, okay, which will be lying at a particular, it will be cutting the solidus line at a particular point which is parallel to T0, which is parallel to T0. Now, if you draw a horizontal line, okay, if you draw an horizontal line, it will meet the liquid line at a point Y. And if you drop it down to get the chemical composition C2, okay, C2. So this point, okay, these 2 points, this graphical line will be partitioning the in between solid plus liquid mixture. Okay, now see here. We draw a horizontal line. This horizontal line is called tie line at the temperature of interest T0. Okay, when any temperature T0. Tie line is the XY line. Tie line is this XY line. Note that the lines can be drawn in the two phase composition region only. Only within this region you have to draw. To find the fraction of solid and liquid. Okay, for example, if you take what composition of solid is there, what composition of liquid is there, to find that composition, we will be using lever rule that we have told you already. Okay, the portion of the horizontal line in the two phase region is like a lever. Okay, it's like a lever with a fulcrum at the nominal composition. Okay, lever, this will be acting like a lever with the fulcrum acting at the normal composition. Okay, so the opposite arm will be a lever and it will be fractionally solid and fractionally liquid phase. Okay, so this, what you can say it is, Up to this is solid phase. Okay, up to this point it is solid, and up this much is liquid. Okay, so that's why we call it as solid plus liquid mixture. Okay, mainly there are two rules. One is a chemical composition, and the other one is a relative amount of each phase. Okay, now you can see it. As I already told, it will be like a fulcrum. Okay, it will be like a fulcrum of a lever. It will be like a tie line. Tie line will be a fulcrum, and this portion will be corresponding to arm of the lever. This portion will be corresponding or proportional to the liquid state, and this proportional will be proportional to the solid state. Okay. Okay. So mainly if you see, the fraction of liquid is F1 is C0 minus C1. Okay. The fraction of solid is C2 minus C0. Okay. So you can get the absolute value at a particular temperature T naught also. Okay. So that is what this tie line principle and phase rule is all about. Now if you take for a composition C0, if you consider at T0, if you consider both liquid and solid phases contain both the elements A and B. Okay, contain both the elements A and B. The state will be in a solid. Okay, it's not, as I already told, it is not a semi state. It will be having some amount of liquid. Okay, solid and liquid in it. Okay, for example, if you take delta T. Okay, if you take delta T, a difference. Okay, in this difference, if you see if you draw a path, okay, the upper path is nothing but the path by the composition of the liquid, this path. Okay, this is a delta T. The path transmitted by this will be a what you can say, the path followed by a liquid portion. This path we call it as the path followed by a solid portion. So this line will determine the percentage of solid and liquid in a particular solid solution. Okay, are you following? Hello? Hello?
Yes, sir, following.
Yeah, yeah. Okay, so like that, many improvements can be done in this phase diagram. Here, what happens is, see here, within that delta T itself, we are subdividing the within the delta T itself, we are subdividing the solid plus liquid mixture. Okay, so okay, so what happens is here in that region, this dendrite formation will be controlled by the amount of temperature T, which is there in between the solid plus liquid mixture. Okay, so and that too in between the liquidous line and the solidus line. Okay, that too in between the liquidous line and the solidus line, and based on the composition. Okay, based on the composition which is present in the weight percentage B, the various elements. Okay, T2, T3, T4, the various elements which are formed can be classified. Okay, the various elements which are formed can be classified. Okay, in above if you see it is liquid solution, below if you see it is a solid solution grains, okay, grain structure. But in between it will be a solid plus liquid mixture or state. Okay, start. Okay, state. So this is another. Okay, this is another form of a phase diagram. The same thing, same. Within that delta T, we are taking three different temperatures now. Okay, three different temperatures now, and we are analyzing the liquid state x1, x2, x3, solid state y1, y2, y3, and the constant medium is at 70-30 percentage. Okay, now if you see in the uniform liquid, if you see the structure, it will be like this. Only liquid will be there. But if you see it in T1, T degree Celsius, T means here. T means very small, very small amount of solid particles will be there. But if you go to T1, that solid particles will be combined together and form a looping structures. Okay, form a looping structures. And finally, still more it happens, and if it combines, a new alloy will be formed. A new solution will be formed, like 70 nickel, 30 copper. Okay, like that, a new solution will be formed. So that solution, based on the percentage, we call it as 70 nickel, 30 copper. So 70 nickel, 30 copper solution. Okay, so that is the result. So mainly when you talk about the equilibrium cooling, that is why we are doing the cooling in the equilibrium state. Okay. So mainly the thing, as I told here, is when the solidification begins, only the primary dendrites will be formed. Okay. Primary dendrites means when in a solution, if a solid is introduced, if a solid is introduced, that solid will be forming a dendrite-like structures. Now, when it is still more heated till temperature T2, what happens is that dendrites will be joining and it will be forming a loop around it. Okay, it will be forming a loop around it. That loop may be either zigzag or any unpredictable nature also. Okay, but it should be free to move. Okay, free to move. Okay, diffusion coefficient should be very higher. Okay. So as I told you, binary phase diagram may take place in three when there happens three types of conditions. Okay, first one is a vacancy mechanism, like here. See here, here this is an atomic structure. In that atomic structure, if you see, there is a vacancy. Okay, any element, any extra element or element from the crystal lattice itself can come and occupy the particular place. Interstitial means in between the atomic structures, like this, it can occupy the space. Similarly, two atom interchange means either any of the two atoms will interchange among itself and it will form a new compound. Okay, four atom interchanging also possible. Okay, just a minute, just a minute. Yeah. So these are the various diffusion mechanisms. Okay, this is the equilibrium cooling, non-equilibrium cooling, which we have already seen. Okay. Now what happens in non-equilibrium cooling is, since the diffusion is very slow, okay, very slow, to keep it within the space with whatever the time period which we have, within that space, if you want to keep it and form a uniformity in the solid, okay, the average composition we can take it as alpha 1, alpha 2. When the temperature drops, the average composition also will be departing still further. Okay, so the solidification will continue only after a higher temperature or a core to form a core structure. We can say it as a core structure. Usually the higher melting center region, we call it as higher melting center region surrounded by lower melting region. Okay, like this. See here, cooling under liquid equilibrium condition. As I told you, non-equilibrium, equilibrium. In equilibrium condition means it will form a homogeneous solid solution like this. Okay, dendrites will be formed and the loop over dendrites will be formed, and they will be still more further, and they will be joining together to form the grain boundaries. Okay, so that solution we call it as a homogeneous solid solution. Okay, but if you take this what you can say, and another format of non-equilibrium cooling, which is nothing but a fast cooling or a rapid cooling, so as to say, what happens is sudden formation of solid structures will be there, but that solid structures will not be distributed properly. It will be having some disturbances, and it will be one material will be in the outer and the other material will be in the inner to say, so that heterogeneous, what you can, heterogeneous mixture only possible. Okay, heterogeneous mixture only possible. Okay, so as the crystal grows, what happens is there will be a difference in the chemical composition from the center till the outside. Okay, from the center point till the outside, that the chemical composition itself will be changing. Okay, usually the chemical composition within a particular alloy will not change, but here in this fast cooling or non-equilibrium cooling, it will happen. Okay. Now this is another example of copper nickel state, wherein it is being heated in a non-equilibrium condition. It is happening, wherein it will be having 35 percentage of nickel and 65 percentage of copper alloy. Okay, just a minute, just a minute. Okay, that nickel 35% and copper 65%, we call it as this 35 and 65. Okay, so wherein this 35, 65 for different compositions are available. So there, from there we need to do segregation. Segregation is non-uniform distribution of elements within the grains. Okay, then the boundary should be not weaker. Okay, if it is weaker, it should be reheated or subjected to treatment to achieve a good solid structure. Okay. This is what I told you. Inside it will be easily solidifying, but outside it will take some time to solidify. But in this, what you can say in the next category, in the previous category of equilibrium conditions, a uniform structure will be formed. A uniform structure solubility will be achieved from the SEM image itself. It will be clearly visible. Okay. Then what is homogenization? Homogenization is nothing but it will be forming along the grain boundaries only. It will be forming along the grain boundaries only. The grain boundary will be always a comparatively a weaker component, but the properties of this is a lower melting point. Okay, so that lower melting point can be used to get a uniformness in the mechanical or the physical properties, okay, of a system. Okay, so that point, okay, that point can be used to utilize it in the physical or the chemical part of the system. Okay, to improve its properties correspondingly. Okay, so slow freezing from the liquid state. Okay, slow freezing from the liquid state. Okay, you should not do what you can say immediate cooling or a sudden cooling. Slow freezing from the liquid state will be resulting in a larger grain size, and it will be requiring a very long time. Okay, but homogenization, if you see, it is a diffusion model of solid state. Usually, it will be an industrial preferred because it will not take that much time. Okay, now if you see here, this is another example of nickel copper only, same example only. The alloy is reheated. Okay, below a suitable solidus line, it is reheated. Okay, it is reheated. So diffusion, okay, since it is reheated, the diffusion will be comparatively homogeneous and it will also be rapid. Okay, it will also be rapid. So the liquid as solid as line and the solid must liquid mixture, that boundary should be deciding the shape and the properties of the system. Okay, the shape and the properties of the system. Okay, this homogenization I already told you. Okay, okay, here what happens is only this we have seen before heating, but after heating what happens? Okay, but after heating what happens? The dendrites which are formed have been disappeared. Okay, only the grain boundaries are visible, which prohibit or hindrances the formation of deformation. Okay, so what makes it to become harder? Okay, what makes it to become harder? Okay, again the dendrite structure will be coarser. Then it can be silk cast or whatever the casting you need, you can do it. Okay, so this kind of structure which is formed out of the heated chemical alloys, we call it as the homogeneous format of alloy mixture. Okay, so these are the properties. See here, the composition of the nickel is changing. Okay, the composition of the nickel is changing. It is increasing from 0 to 100. Simultaneously, the tensile strength is also increasing up to a certain point, 50,000. It is increasing, then it starts on decreasing. Similarly, the elongation, if you see, it is decreasing. But here, in this what you can say, electrical resistivity and parallel hardness, up to a particular point, it goes on rising, then it will be reducing. Okay. Okay, so that is an example of this thing. Next, the properties of the solid solution. We told you that two elements are mixed and we have formed a solid solution. Okay, how that properties of that solid solution will be depending. Okay, how the properties of that solid solution will be depending. Usually, if you see, electrical resistivity will be depending upon the distortion of the lattice structure. Okay, since the distortion increases, okay, increases with the amount of solute metal which is added, and since either the metal can be considered as the solvent, the minimum electricity resistivity will be occurring in the center of the composition range. Okay, whatever the composition range, if you take the minimum electrical resistivity will be happening in the center of the composition range. Okay, as like copper, the tensile strength copper to nickel, the strength also can be increased. Okay, by increasing the amount of nickel. It's not nickel, it's especially the element which is contributing to more strength. Okay. Approximately two-thirds of nickel and 1/3 of copper means this is a commercially available alloy known as Monter. It shows a good strength and a good ductility along with higher corrosion resistance. Okay. There is also these type of pseudo eutectic alloys. Now, if you see it here, okay, if you go on increasing the composition, at one point it will become zero. Then it will be going on increasing. Okay. Similarly here. Okay, but these kind of structures are very rarely found. Okay, the solid solution which shows a minimum, the solid solution which shows the maximum. Okay. Okay, variation of type 1. Okay, now if you see, each alloy in a type 1 system has a melting point. Okay, has a melting point between melting points of A and B. Okay, that is alloy mixture. Usually it will be possible for a system in which a liquidus and a solidus line to get the maximum and minimum easily. So from the phase diagram, that maximum minimum solidus liquidus can be easily achieved. Usually there will not be any difference in the material composition. Either it will not change from liquid to solid or solid from liquid, but be careful. Okay, the solidus is a constant temperature with no much change in the composition, and the cooling curve with respect to horizontal structure. Okay, horizontal thing we call it as a concurrent type of metal alloys. Okay, concurrent type of metal alloys. Next is a phase rule. Phase rule is nothing but, as I already told you, the number of degrees of freedom will be F, number of components will be C, and number of phases will be P. Okay, they are closely related with each other. So number of degrees of freedom will be equal to C minus P plus 2. Okay, the number of external forces is 2. If there is no external force and only a your medium only, that is appreciable effect of our phase, whatever the phase that we are giving, that when we can go for F equal to C minus P plus 1. Okay, C is nothing but number of components, F is nothing but the number of independent variables, or we can say it as independent factors. Okay, independent factors. So what is degree of freedom? Degrees of freedom is nothing but the ways in which a system can respond to a output. Okay, system can respond to a output. So whatever we have seen till now is only type 1 type of category of phase diagrams. Type 2 we have already told you, that is two metals are completely insoluble. However, in some phases there will be a some cases. Okay, there will be a solubility in practical purposes, which is mostly impossible. Okay, for that only we are having Rowlett's law. That is, the freezing point of a pure substance should be lowered by the addition of second substance, which is soluble in that first one. Okay, and a pure substance will be solidified. Okay, the amount of lowering of the freezing point is proportional to the molecular weight of the solute. Okay, so these I know. Okay, these I told you. These are the series of cooling curves drawn, and the phase diagram. Okay, solid plus liquid as mixture is drawn like this. Okay, these are the various structures. See, here it will be still clear. Two metals completely soluble in liquid but insoluble in solid state. So this is the phase diagram for type 2 type of components. Now if you see it in the bottom, it will be solid A plus solid B. Above it is liquid. So this gap will be liquid plus solid, and this gap will be liquid plus solid A. Here it is solid B, here it is solid A. Okay. Mainly when you take two metals and it is completely soluble in liquid phase but not soluble in solid phases, solid state, so as to say. Why? Mainly it consists of four areas. Out of that four areas, three areas are two phase areas. Okay, three areas are two phase areas, two x, y, and z axis. Okay, and it represent only a single axis. Okay, single phase, and that it is a pure metal. Okay, that it is a pure metal. Okay, since the two metals which we are taking it for combining are assumed to be insoluble in nature, means then it is very easy. Comparatively, it is very easy. Okay, these are the still more complications wherein here we are adding another state called eutectic plus solid state, solid A plus eutectic mixture or eutectic state. Okay. So the point E, where it is this corner point, this intersecting point E, since this point is the intersection of liquid and solidus line, what happens is the liquid will be now starting to solidify. Okay, the temperature cannot drop until the alloy is completely solid. Okay, it will mainly that solidification process will happen in two phases. That is, in the one, it will be appear at the either end, and in the other, it will be appearing as a eutectic mixture. Okay, eutectic mixture, which will be resulting in a very fine mixture visible to visible under the microscope. Okay. Similarly, this is a liquid type of soluble in liquid but insoluble in the solid, means in liquid container or a beaker, this will be heated. Okay, this will be heated and it will be converted. Usually, the melting point of this alloy is very lowest than the considered phase diagram. Okay, this is another two metal completely soluble in liquid but insoluble in the solid state like this, wherein the microstructure of the lead tin alloy, okay, of a eutectic composition, the microphase will be consisting of a variety of phases like alpha phase, beta phase, etc., which is shown here. Okay, wherein the eutectic structure for the lead system is shown, and the direction of diffusion also it's clearly indicated by blue color and red color and even green color. Okay. So we told you there is a particular chemical composition and temperature graphs are there. But how to find the composition or how to find the temperature is, see here. At all the point of liquid L1 is saturated at A. Okay. At the point liquid L1, okay, it is saturated at L. Is saturated in area A, but the temperature is dropping slightly. The excess A can modify or solidify the component. Okay. So by depositioning these crystals of A must be richer than B, okay, wherein you will be having this formula and you can find out A and B, okay, the point at which it will be colliding, okay. So these are the various solids which are nothing but two metals completely soluble in liquid but insoluble in the solid phase, okay. Now if you see this, the alloy will be consisting of 67% of grains and 36% of eutectic mixture, okay. Then as we move, okay, see here, as we move to the right, completely it 99.5, 2.8, 12, 20, 50, and pure silicon. So at different temperatures of silicon and different temperatures of aluminum, the material will be behaving differently. Okay, the material will be behaving differently. Okay, this is a complete phase. Okay, and these things are very important. How the liquid changes in the system will be changing. From a liquid solution, it will go to a solid dipped on a liquid solution, then it will go to a solid. Okay, below it is a water, liquid plus alpha, above is a what you can see. An imaginary thing. Okay, imaginary thing. Here you can see an alpha, and here you can see L plus alpha, and here you can see a liquid. Okay, so by using these things, these percentages, we can also calculate the composition. So I told you X2L2 by T2L2. The same thing we can take it here. Yeah, see here, alpha percentage will be equal to, alpha is where, here it is alpha plus beta. So alpha 20%. Yeah, alpha if you take it as 20%, 20 divided by 70. Okay, this is 20. Okay, 20 divided by 70 is alpha percent. EF where it is EF will be 71.4. KJ will be 29.4 where it is. Then HK will be 70.6 percentage. So at eutectic temperature or at room temperature, how it will behave? What will be its temperature? Okay, that is very important.